Greetings, this is Chemistry with Nav. In today's video we're going to look at buffer action. So I've found a question which is quite typical to A2 papers, and it says describe how to make a buffer solution from ethanoic acid and sodium hydroxide solutions. Explain how the buffer resists changes in pH on addition of small amounts of H+ or OH-. Well, it's a little bit unusual to make a buffer solution from a weak acid and a strong base, but it's perfectly possible. So the first thing to do is to write an equation for that reaction. So we have the ethanoic acid and the sodium hydroxide, and that's going to make the salt, so CH3COONA, sodium ethanoate, and water, which is with an H. So what I've actually done there is I've created the salt of the weak acid in situ, which means within that actual reaction itself. So the second part of the explanation has to be that the weak acid must be in excess. Because if we have the weak acid in excess, then we actually have some left over. All of the sodium hydroxide gets used, and all of the sodium hydroxide turns into sodium ethanoate. Therefore, we have some quantity of the salt, but we also have this leftover excess acid as well. And that's where our weak acid and its conjugate base, or its salt, come into contact with each other. So that explains the first part of the question. The second is about the actual action itself. And I would suggest this goes in sort of three sections. So one, you write the equilibrium, and that's the equilibrium of the weak acid. So CH3COOH in equilibrium with CH3COO- and H+. Because that sets us up really for everything else that we need. That's usually also the first mark in that question. Remember, the acid concentration, so the species on the left-hand side, is coming from the original ethanoic acid. Very, very little of that dissociates. So we artificially boost the conjugate base concentration by adding the salt to it. So we actually have quite a high concentration of both the acid and its conjugate base in that equilibrium. The second part is to say on addition of H+. We actually get a reaction. So we don't write it as a reversible reaction. We write that the H+ combines with the conjugate base to reform the acid, CH3COOH. But basically what that's suggesting of the equilibrium in part 1 is that the equilibrium shifts left. So that's what we write. The equilibrium shifts to the left-hand side. And what that does is that basically ties up any of the excess H+ or the additional H+ that was put into the system, and therefore it doesn't affect the pH. The last thing to write is about the OH-. So on addition of OH-, the H+ from the equilibrium on the right hand side reacts with the OH-, and that goes to form water. But if I take the H+ out of that equilibrium, that means that the equilibrium will seek to replace it. So the equilibrium shifts to the right hand side. So I can take some of the H+ from the equilibrium, I can react it with the OH- that was added, that combines to make water. So the OH- is used, and therefore the pH doesn't change, but some of the H+ is also taken, but that will be replenished by the equilibrium. So what we have here is sort of two sections. Very often this is asked as a 5-mark question, and the 5 marks would be 1, 2, 3, 4, 5. Sometimes it's a 7-mark question where you will then have the additional 2 parts above.